Hi, everyone. Welcome to Lecture 9 of Intro to Modern AI. Today, we're going to talk about some aspects of neural network implementation. First, we're going to talk about optimizing neural networks. So we're basically going to look at the different aspects of a neural network model, the model itself, the loss function, and the optimization. And we're going to actually run through what that optimization now involves, really just plugging in what we've done so far with defining gradient descent and those sort of things into the case of neural networks. So optimizing a neural network. And this is going to lead us to a few issues that kind of crop up when we deal with neural networks. And so specifically, we're going to talk about optimization, or we're going to talk about really gradients and initialization. So we're going to use the gradients, of course, to actually make our optimization updates. And we'll see that unlike in the case of linear models, how we initialize the actual weights for a neural network model really does matter and will have a big effect on the optimization performance. And so we're in fact going to sort of go through how we typically initialize weights in a neural network. And then finally, we'll talk a little bit about PyTorch mechanisms and sort of PyTorch design. And this is basically going to be just an exercise in going over some of the basics of PyTorch, not just how you use the automatic differentiation tools, but how you use the neural network library and how sort of you typically structure layers in terms of modules and parameters and things like this. Now, in your homework, you're actually going to use very few pre-built layers of that library. You're going to basically implement everything yourself, but we're still going to use kind of the idiomatic PyTorch code in order to actually implement these things yourself. All right, so that's our outline for today. Let's go ahead and jump in. And let's start off by talking about optimizing a neural network. Okay, so what is a full sort of, what are the three ingredients, again, coming back to these one more time, or many more times, we're really going to come back to them. What are the ingredients of a full machine learning algorithm using neural networks? Well, number one, we have our model, which in this case is a neural network. And what we mean by that really is just we're going to have our model function of x be equal to, in this case, we'll just consider a two-layer neural network. So it's going to be equal to W2 times some nonlinearity, say the ReLU nonlinearity, you just take the max of the number and 0, of W1 times x. Right? So that's going to be our function here, where, of course, x is a vector input, and W1 and W2 are properly sized such that these multiplications all make sense. Secondly, we're going to have our loss, which is the cross-entropy loss. Entropy loss. And this is just defined, and I won't give the whole derivation again here, but this is going to be defined as the loss between our predicted output and our desired output here is just going to be equal to the negative value. Again, you can derive this by looking at the log of the probabilities, or interpreting the outputs as probabilities under the softmax distribution. But really, I'm just going to define it like this, plus the log of the sum from j equals 1 to k of the exponential of hx k. Barely fit it in there. Okay, so that is our first two elements, the model and the loss. And the third is going to be our optimization procedure. And this, as we discussed, is really just going to be the same as before. It's going to be stochastic gradient descent. And then we're going to use sort of mini batch stochastic gradient descent here to be clear. But beyond that, I want to kind of take a look at what SGD here really looks like. So here is sort of what the actual SGD update would look like. We first, number one, would initialize. Let me write, this is actually what stochastic gradient descent looks like. Gradient descent. And it looks something like this. So the first step is that we initialize our parameters, the things we're optimizing over. And in this case, that would be W1 and W2, these matrices. Now, before, in a linear model, we just set this to be equal to 0 for stochastic gradient descent. It turns out, for reasons that we can't see, I'm not going to write that here because, in fact, we can't do that for a neural network. For reasons I will talk about in a moment in the next section, we can't actually just initialize our parameters to 0. And so we're going to have to initialize them somehow else. And we'll defer discussing that until the next portion of this, but just know that is coming. We're going to talk about initializing these. And number 2, we're going to repeat for t equals 1 to the number of epochs. And then we're going to repeat for each mini batch. This is mini batch, I should probably clear, this is mini batch version of SGD. For each mini batch, x we define this as b and b by n. And the true y, which has values 1 to k, and it has b of these in the batch. We're going to form, oops, I'm kind of cutting off the text there. Let me move this over a little bit. Let's see if I got it all. Oh no. All right, I'll move it over here a little bit for the sake of clarity. Okay, so what we're going to do then is we're going to perform our update. And we're going to take a gradient step over all the examples in that batch. But when we say a gradient step now, before we sort of framed SGD as just taking an update to the parameters in terms of their gradients. And what that means here is we're just going to update both parameters, W1 and W2, by making an update in terms of their gradients. So here's what I mean by that. We're going to take W1, and we're going to set W1 equal to W1 minus the step size times its gradient, the gradient of the loss that we care about here. And because now there's some ambiguity as to what we are differentiating with respect to, I'll sort of write this gradient symbol with a subscript of W1 just to make it clear that we're optimizing that with respect to we're taking the gradient with respect to those W1 parameters. But all this is here is 1 over b times the sum from I equals 1 to b of the loss. And I'm writing a little bit small here so I don't run into my head here in the video. But the loss of our model applied to the ith example in the batch. Again, I won't notate that, but here xi denotes the ith example in that mini batch. And yi. And then similarly, for W2, we're going to set W2 equal to W2, W2 minus eta times the gradient with respect to W2 of 1 over b, sum of I equals 1 to b of the same thing, right? The same exact loss. The only difference here is that we're taking the gradient now with respect to W2 instead of with respect to W1. But kind of when we wrote in the last slide, when we wrote kind of the form of stochastic gradient descent where you sort of make one gradient update, of course, when you have multiple parameters, you have to make multiple gradient updates. And that's just the mechanisms of how gradient descent works. Okay, so this is the basic idea of what we need to do. But again, there are some challenges here, right? Let's ignore for now the challenge of sort of computing these gradients. Of course, that looks much harder, but what we sort of found out last time, right, is that we can just use PyTorch to get all of those gradients. In fact, we'll see that later on, how we kind of do that a little bit, or how we can nicely do that. You'll, of course, really implement it in the homework, but we'll get a sense of sort of a slightly more PyTorch way of doing this. But these gradients at a high level are just going to be computed via the automatic differentiation tools of PyTorch. What we do care about, though, in this setup, And also, this sum here, we won't explicitly write as the sum. We would write it in a more efficient form for PyTorch to optimize. But again, those are all just kind of details. And we won't go into those again. We covered that a lot kind of in the last couple lectures. A lecture on training a linear model, at least. What we are going to care about, though, is this term, which is how we initialize the weights. Because it turns out that unlike linear models, as I said, where we just could initialize these things to 0, when you use a neural network, you no longer can just initialize these things to 0. And before I show some examples of this and kind of highlight what we're going to do instead, I just want to give a quick illustration of why this is the case. So I'm going to write some sort of terms of a simple derivative here. Well, first of all, let me say I'm going to talk now about gradients and initialization. And I'm going to consider a really sort of simple function which ends up being part of our neural network, though it's of course a much simplified version. I'm going to consider just, in fact, the model itself. And I'm going to even make a further simplification just to make this point and assume for right now that everything is just scalar valued. And in fact, we don't even have an activation. Of course, this would all hold the same if we do have a nonlinearity. So this is actually a linear model. I mean, and as we saw, it's sort of equivalent to a normal linear model because you can just, of course, combine these two terms into one. But the interesting thing here is when you actually look at the gradients and the derivatives of this function with respect to the parameters, it is in fact different from a linear model. So let's just think about this for a moment. Let's think about what the gradient would be. This is actually all scalar values. So here I should just mention that, let's say that W1, W2, and X, of course, are all just scalar valued. So this is a function that just maps a real valued number to another real valued number. We now can compute the parameters, we can compute the partial derivatives of this function with respect to our parameters, W2 and W1. And it's a very simple math here, right? All that you would say is that the partial derivative of our model with respect to W1, well, that would just equal W2 times X. And the partial derivative, similarly, without nonlinearity, it's rather boring here, but the partial derivative with respect to W2 is just equal to W1 times X. But something kind of interesting happens here, which is that if we were to, and I know these are just sort of partial derivatives, they don't include the loss function here, but if you think about it, these derivatives will, by the chain rule, they will appear in the loss itself, and so, or the derivative of the loss, if we apply a loss to this. And so these terms do occur in the actual gradients of our loss with respect to the different neural network parameters. It's just a much more simplified setting here. So terms like this kind of do occur in our full gradients. And what's interesting here is that if we initialize, so if we initialize W1 and W2 to 0, then both the derivatives are also 0, right? Because they both involve a W2 term or a W1 term. And this same thing holds for neural network models. If you, and you can try this out in PyTorch if you're curious, if you initialize your weights to be equal to 0 with a neural network model, what you will find is that, and there's a few other conditions, but say you use the ReLU activation with a nonlinearity, then what you will find is your gradients are also 0. So that means these two terms here, if you initialize W1, W2 to 0, these two terms will also be 0. And that's not very good, because obviously, if they're both 0, you will not actually perform any update on your parameters, right? You'll just be stuck at 0 forever. What this actually corresponds to is the fact that 0 is a local optimum, or really rather it's technically a saddle point, but we're not going to worry too much about these distinctions for now. It is a point where the gradient is 0. Yet it's not a very good point. Of course, you're not making very good predictions when you just have all your parameters equal to 0. And so in order to actually perform optimization in a neural network, we need to initialize our parameters to something other than 0. I'll just also make the point here that if we didn't have, I'll erase this in a second, if we didn't have HW2 there, then obviously this gradient here would just be x, and so that would be non-zero whenever x was non-zero, right? But having those two sets of parameters makes this quite a bit tricky, quite a bit trickier. All right, so the question is, what do we choose as the initialization for W1 and W2? And what we're going to do is we're going to use random initialization. I mean, we could find deterministic ways of doing this as well, but there are various reasons why random initialization is nicer. And so instead, we're going to use random initialization. And one way we often write this is we say that W1 is sampled from, say, a normal distribution. This is the symbol here for a normal distribution. I will show, this is just the, for example, this is just the torch.randn call. It's a normal or a Gaussian distribution. It will be initialized to, or as a first guess, it'll be initialized to a normal distribution with 0 mean, so it's centered around 0, and some standard deviation, or some variance, we call it. And in fact, we're going to start off, this is not going to be the final number, but we'll start off with just this being 1. This is exactly corresponds to the torch.randn call. So if you call torch.randn, it will exactly create a random variable that, or a set of random variables, a whole matrix of random variables, in fact, for all the with mean 0 and variance standard deviation 1. For this class, you don't need to know hardly anything about normal distributions. Everything I'm going to sort of demonstrate right now can in fact be derived formally by looking at kind of the properties of random variables and using a technique called the central limit theorem. I'm not going to do any of that. I'm just going to provide kind of an incredibly empirical and maybe unjustified, but slightly empirically justified approach to what we're doing. But just know this is sort of the calls I'm making. And really what I mean when I say W is initialized according to this, what I mean is that each element, say Wij, this doesn't mean sort of W1. This just means each element of every matrix W would be initialized as a normal random variable. But then there's a big question if we do this. So that something comes, if we just do this, there in fact is a problem. And in order to sort of illustrate what this problem is, I'm going to demonstrate kind of what happens to a set of inputs X as you multiply it by a sequence of matrices, or maybe just even one matrix, with these random values. Okay? And in fact, as a starting point, we're also going to assume that X itself is going to be normal 0, because X can take on sort of any distribution, right? X is, the inputs, it's pictures, it's whatever else. But it turns out it's actually quite useful to think of it as being normally distributed, at least initially. It will wind up being the case that it won't really matter what the distribution of X is, but again, just for the sake of sort of making this concrete, I'm going to start with a normal distribution. All right, so let's jump over to our code here, and let's set up this thing, because really this is all going to just be a very empirical demonstration. So I'm going to import torch, going to import math library, and import matplotlib as plot. Okay, and I'm going to initialize my X. Let's say n here is, I don't know, we want enough variables here that we can actually view these things in terms of sort of histogram plots. So I'm going to make a fairly large high-dimensional X. Maybe it's not that high-dimensional, but still bigger than what we've been dealing with so far. All right, and I'm going to set x to be torch.randn of this many random variables. So here x would be a 20,000 dimensional vector, and just with random entries in it. So let's look at what this variable looks like, and I'm going to do that by plotting a histogram. So this is going to plot a view of basically how. I'm actually going to also do one thing here. I'm going to get rid of that output. This will plot here. This will plot kind of a histogram of the different values x takes on. And if you do happen to be familiar with normal distributions, this is a standard looking normal distribution. At least it's not quite perfect because we don't have that many elements, but this is a standard kind of bell-shaped normal distribution centered at 0, and the standard deviation here is 1. We can actually even look at that, so I can print x.standard. And that is about 1. It's not perfectly 1 because, again, there is some error in the number of samples we have. And all that means is that, about 2/3 of the data is within the range -1 to 1 for a normal distribution. Okay, so this is sort of what our initial data looks like. And now we want it to be the property that as we apply subsequent operations in our network, we would like things to stay roughly distributed in this same fashion. Okay, so we would like it to be the case that we have roughly the same kind of distribution for our subsequent values in the network. And the reason why this is, and so what I mean by this, just to be clear, maybe I'll go back to the sheet for a second, my slides for a second. What I mean by this is, we have our input x that has some distribution. And again, it won't actually be normal, but let's say it was normal. It will turn out, I'll show you in a second, that actually it doesn't matter what the distribution is, as long as it's 0 mean, or even if it's not 0 mean, in fact, you'll get the same kind of inputs. So as long as this is sort of normally distributed, or even doesn't really even in fact matter what it is, we would like, and what we're going to do in a neural network is we're going to sort of apply a bunch of operations here. So we had this neural network, but maybe we have subsequent deeper layers too. We would like it to be the case that all of these successive applications of linear layers that say it's, at some point, obviously with the nonlinearity, you can't really be normal after that, but we would like it to be the case that, say, after this step here, let me actually just note this, after this step here, and maybe also after, well, I'll write a few here. So we would like it to be the case that after this step here, or maybe after this step here, or many other things, we would like it to be the case that these elements were roughly normally distributed. It doesn't have to be perfect, but we kind of want them to not sort of blow up in value. Because if the size, the magnitude of our activations is getting bigger and bigger at every layer in the network, then we have a problem, right? Because if that were to happen, then maybe we'll run into numerical issues as we get deeper in the network. Maybe we would also, actually, it is in fact the case that if this happens, you wind up having very differently scaled gradients, right? Because the gradients involve sort of these subsequent terms as you go through the network. And so you wind up with sort of very badly uneven gradients that make your parameter updates very different. So for all sorts of reasons, we would like kind of all of these sort of different intermediate activations in the network to be roughly similarly scaled. So how are we going to accomplish that? Well, we're going to accomplish that by, again, choosing random weights. But let me show you what happens if we just choose our weights to be truly random here. So I'm going to set W here to be equal to torch.random, and let me pick just some random other quantity here. I don't want to make it the same as n, because I want to emphasize that these are different quantities here. But I'm going to now look at, I'm going to say z equals w times x, and I'm going to look at a histogram of z, and I'm also going to print the standard deviation of z. And what we see is that this is going to wind up being much, much these values take on much, much larger magnitudes. So here's my histogram. The important point to realize here is the x-axis. This shows sort of how many points are within each bin. And this is a much, much larger range of points than we have for our input, right? Our input range between, -3 and 3, almost all the points. This one ranges between -400 and 400. So what's happening, kind of not surprisingly, is because all the entries of this are rather large, right? All of its entries, they're random also, but as we multiply different random numbers together and add them all up, this is adding up on average to a sum that's much larger than our initial starting point. And this is a basic property of random variables. And so in some sense, to correct for this, we need to adjust W. We need to scale the entries of W by some amount. And I won't sort of prove this here, but it turns out the exact amount you need to scale it by winds up being the square root of n. This is a property of normal distributions. The variance is equal to just the square root of, the standard deviation is equal to the square root. Really, with the sum of random variables, the standard deviation ends up being the square root of each variance. And so in order to make this sort of evenly scaled, you have to divide by exactly the square root. We're not going to prove this, but this is sort of a basic property of statistics. And if you take a sort of a basic stats course, you will effectively observe this feature, if not prove it directly. And it comes from basic properties of normal distributions and also from the central limit theorem. Now, if we do this, we find that we actually get, again, a normal distribution that is scaled, right? So now our outputs after this layer wind up being exactly scaled nicely between 0 and, or sorry, I shouldn't say between 0. They have mean 0, but they are the same distribution, kind of on average, as our initial inputs. And the interesting thing is this is actually true kind of in some sense regardless of what our initial inputs are, all right? So we don't need to make W a random normal. We can also actually just make X just be equal to 1s. And now it's just adding up, in fact, all the entries there. Of course, our histogram for X is going to look very different. It's just going to be all the entries are at 1. But it turns out we're going to have a similar kind of output of our distribution because now, in fact, so this is going to be a similar normal distribution because, in fact, all we're doing now is we're just adding the entries in a column of W. So what's very interesting about this is it doesn't matter in some sense what the distribution of X is. What really matters, we're getting our randomness and sort of our niceness of the intermediate layers from the entries of W itself. And that, in fact, lets us sort of play these kinds of tricks. All right, but I am going to go back to making this random. Just note that that's not at all required for this to work. There is, however, one important point that I want to make, which is that, when we have our first layer in the network, so for, this might make sense as a, as an item for, say, this layer, right? So maybe that makes sense as a way to scale W. But there's a problem here. And the problem is if we apply, say, the ReLU nonlinearity. So I'm going to say, so let's say that sigma of Z equals the max of 0 and Z. Again, that's just this function that looks like this. It is 0 up until this point, and then just a linear line there. Okay, so if we make this our nonlinearity, this is a very common nonlinearity in a lot of networks. Then let's think about what we're doing with our weights here. Well, in this case, when we multiply X, so I'm going to start by making maybe this, rather than just having this be torch.randn, I'll have this be torch.ReLU of randn. Now the histogram is going to look a bit different here because what we're going to have is the second half is actually going to be all the same, but every entry that is 0 or less will become 0. And so this will in fact be have a big spike at 0, and then you can't quite see it is actually half of a normal distribution here at the bottom. And now what happens if we multiply this? Well, it turns out that essentially half I mean, we're multiplying W here, each row of W by every entry of X. But half of those entries are essentially 0, right? In other words, we have kind of decreased the effective input, the real input dimension in some sense, by 1. And in order to undo that, and if we actually run this, we'll see that our standard deviation is in fact less than 1. And so we're getting our elements too small. If we keep doing this, they'll keep shrinking and shrinking again. So in order to keep this consistent, we actually have to not divide by the square root of n, but actually the square root of n divided by 2 to account for the fact that half of our entries are 0. This is often framed, just for the sake of it, as multiplying by the square root of 2 over n. Those are, of course, the same thing. And we see when we do that, after a ReLU, we have, again, a standard deviation of 1. So if we go back to our sort of model here, if we keep applying these things, so if we have these parameters, I guess the first one, in theory actually could be 1 over the square root of the input dimension. But in all subsequent layers, we kind of want, and if we use this ReLU nonlinearity, we want our weights to be equal to, we want each element of the weights, and I'll write it kind of as W, well, I'll write, just to be clear here, I'll write, WL, that's the Lth layer. We want the ij entry of that to be equal to this random, I'm going to use a kind of weird notation here a little bit. You can write this in terms of the second term, of course, but I'm going to write it like this. This random normal value, but then times the square root of 2 over the input dimension, whatever that input dimension of that matrix is, right? So that's going to be the initialization we use. This is sometimes known as the He initialization. For Kai-Ming He proposed this as or at least popularized. Let me write this somewhere. Oops. This is called the scaling it this way, sometimes called the He initialization. But a lot of different sort of similar techniques have been proposed for a long time, and this is essentially, a fairly common technique. Now, it's important to know that sort of this 2 factor here is specific to this ReLU nonlinearity. So it turns out that for other nonlinearities, you might need a slightly different constant there, but the idea is you actually can find the correct nonlinearity for every single possible kind of, really for every single possible nonlinearity, you can derive what that constant should be. All right, and that actually is it. If we now start with this process, and I'll just sort of write this here, I'll annotate this and say randomly, but with with proper scale, then in fact this procedure all works. And that will in fact be the way we apply stochastic gradient descent for our neural network models. All right, so finally, I want to talk about one more thing, and this is actually going to be entirely done here. This is going to be about PyTorch mechanisms. And so now I'm going to show you kind of how we typically implement things like this in PyTorch. Of course, you're going to do this on the next homework 3, and you'll play with sort of a PyTorch implementation. You'll actually implement really most of these layers, all these layers, in fact, from scratch, but we'll still sort of use these typical conventions of PyTorch as a way of writing our code. So let me switch back to this. And now what I'm going to do is I'm going to import not just PyTorch itself, but I'm going to import a library called torch.nn for the neural network library, and I'm going to call it torch.nn. It's nn. Okay. What I want to show you now is how we specify layers in PyTorch. So layers in PyTorch are defined, and I'm gonna use the example of a simple linear layer. PyTorch, of course, has a linear layer, but we're gonna sort of make our own linear layer. I'm gonna use the example of a linear layer, and this is a layer that encapsulates a single matrix multiplication. And we also want to sort of additionally embed properties of, say, the initialization, how we will optimize, what parameters this layer has, etc. And the way we do that in PyTorch is by subclassing this class called nn.module. And each subclass of module needs essentially two functions to be implemented. It needs the initializer, which in this case will take both the standard first argument of a class, as well as, in this case, for a linear layer, well, the parameters of a linear layer would be the input dimension and the output dimension. You might also want to include, what's the initialization factor? Should it be 1 or 2 or whatever we had? But let's just assume we're going to use it with ReLUs, so we'll sort of do it the way we did it before. The first thing you need to do is you need to initialize the superclass. This will sort of set up all the PyTorch modules. Just make sure not to forget this. Actually, if you forget it, your code just won't work. So make sure to do this. And then I'm going to set a weight parameter in the module to be equal to, well, remember, how did we initialize our weights? Well, we made sort of a random value. It would be out dimension by in dimension. That's the size of our matrix. And we would want to multiply it by the square root of 2 divided by the in dimension. Right? That's how we would sort of set up this parameter within our layer. If you're already ahead of me and know about PyTorch, I'll get to the nn.parameter call in a second, but I'm going to first just define it like this. All right, next what we can do is we can implement the forward function. And the forward function, that's the second function. So essentially the two functions you need to worry about in a module are the initialization, which just sets up the layer itself, and then the forward call, which actually calls the layer. And PyTorch then will actually kind of work out some of the mechanisms such that you can just call this layer on some input, some batch of inputs, and it will work. Now, the convention of PyTorch is that you're always passing batches of examples. So here, X would be an example that has the number of rows equal to the mini batch size and the number of columns equal to the input dimension. So all we will do, and the way you would implement a layer like this, is it will return X times self.weight transpose, right? Because that was sort of our formula for the mini batch form of a linear layer. And that's all that we do here. Okay, so this is actually our linear layer. And what we can do now is we can actually call it. So I'm going to have my layer be equal to linear. Well, first let me make X here. I'm going to have the batch size be 100, and let's have the input dimension be 128. All right, we're going to initialize a linear layer that maps from our input dimension, which is 128, to an output dimension, which will say 256. And now we can look at applying our linear layer to X. And this will output a tensor. And we can look at the shape of this tensor. So this, as expected, the batch size stays the same. And the output size is now 256 dimensions. So again, every row of this matrix X is a different input, and every row of this thing here is a different output. It's important to note that you do always need to call PyTorch layers on this mini batch form. So you can't sort of do this and call it on X, or actually, sometimes it works here. It actually is smart. It's learned to be smart enough. But in general, what you should do is always have the convention, because this won't always work as you have more sort of fancier layers here, and especially as you have larger tensors where you can't just sort of use the same multiplication here. PyTorch does, in some sense, use this convention. The first is always the mini batch. Good to know that it actually does work in either case, though. Learn something new every day. Even when I'm teaching, I learn something. Okay, so what do we? So there's one more element though that I need to emphasize of these layers that is that's important, and that is layers in the first sense, are just sort of encapsulations of kind of operations we use. But layers also keep track of their own parameters. So in this case, the weight item is the parameter of this layer. And the way we kind of track that in PyTorch is we wrap this tensor in this class called nn.parameter. So all you're going to do is you're going to just wrap all your parameters in this parameter class. In fact, what we're really going to do in the homework, and I'll just write this right now, even though it might be a little confusing, because we're not going to allow usage of the NN library in general. I want to demonstrate its usage here, but because we're not going to allow usage in general of this library, we're actually going to import just the module and the parameter class. And so your homework, this will look more like this. So in your homework, it'll look more like this. And you will then have subclasses. There's a subclass of module, and parameters, there's a subclass of parameter, but this is the same thing. Okay, now what we see here is we actually get the same, oops, what's happening here? From torch.nn parameter. Okay, now what we see here is we have the same thing as before, but there's another nice property of this layer that is sort of worth emphasizing here. So now layer, every PyTorch module has this parameter, or has this function called parameters. And that will return a list, or really a generator. So if I want a list, I'll have to convert this to a list. It'll return a list, a Python sort of generator, which you can convert to a list of all the parameters of the layer. So in this case, there's only one parameter of the linear layer, of course, and it is just this one matrix self.weight. But what's nice about this is a few things. First of all, by default, the requires grad property, remember this is the property that told PyTorch to take gradients of a function. The requires grad property is always true for parameters. That way you can just call the model on an input and it will automatically let you kind of take gradients with respect to those parameters. Another nice thing about this is that actually PyTorch modules track also the parameters in their sublayers. So we'll show this in a moment when we talk about neural networks. But it turns out that if you include two linear layers inside of another layer, then actually the parameters of those two sublayers also show up in the parameters of the layer that includes them. And that's very nice because it means we don't have to track each individual parameter. We can just use the parameters call on our entire model and let it basically figure out how much of basically let it figure out how many parameters and what are all the parameters of that model. All right, so just to make this point, I actually want to show you now that this layer is in fact doing the exact same thing as PyTorch's linear layer. So I'm going to sort of define also my reference layer to be this thing, which is PyTorch linear. It also has an just like we created this here, its two arguments actually also happen to be the same thing. So I'm going to take my input dimension, my output dimension. I also need to set bias equals false for a PyTorch layer. By default, PyTorch also adds a bias term, another parameter term to all the layers, which you don't really need in most models, and so we're going to leave it out. But if we do this, what we see is that actually this layer essentially works in the exact same way as our linear layer we defined here. So for example, our layer has a weight, it's a parameter, and it's this size. If we look at the reference layer, it also has a parameter called weight, and this parameter is the same size. And in fact, what this means is that if we set our parameter, if we set rather the values of our parameter to be equal to the same values of that parameter in this reference layer, these two layers will produce the exact same output. So let me just show that. To make this sort of work, you have to do it in a torch.nograd loop because, again, parameters will always track their gradients. So I'm just going to say layer.weight equals ref layer.weight. This just makes it basically copy the values rather than copy over the actual pointer to the parameters themselves. Um, and now if I apply my layer to X and I look at applying the reference layer to X, I see these are in fact the exact same thing, and so all the entries are 0. In fact, I can take the norm too, and this is just 0. So we are in fact creating a layer that is exactly the same, does the exact same thing as this PyTorch linear layer. And in fact, throughout a lot of the rest of the class, what you're going to do is you're going to design layers in PyTorch that wind up exactly replicating so you're going to sort of design layers kind of from scratch using PyTorch, but not using sort of the pre-built ones that in fact exactly replicate those layers in the pre-built and in the pre-built models or in the pre-built neural network library. And that's how we're going to test the accuracy of your implementation in many cases. We're just going to compare it to the PyTorch reference. Okay, so the last thing that I want to say here is this notion I mentioned before about sort of building up larger layers from different subcomponents that are other layers. So let's say I wanted to define a 2-layer neural network, which is again going to be a subclass of module. What I would do here is I would initialize it, and here the dimension is going to be the in dimension, the out dimension, and say the hidden dimension. That's sort of what the relevant parameters are in a 2-layer neural network. I'm going to start by initializing my superclass. It's not doing auto-completion there, so I worry that I'm making some mistake, but we'll see in a second. Then I would say that my first linear layer, which I'll call that W1, would be equal not to a matrix itself, right? Because it's actually, you don't want to always sort of embed every single matrix. You want to use the layers you've built before. So I can define this to be a linear layer. Okay, so I think I'm right again. With in dimensions, with input dimension, in dimension, and output dimension being the hidden dimension of the layer of the neural network. And similarly, self.w2 equals linear with the input of hidden dimension and the output of the out dimension. Right? And that is how we initialize the parameters of our network. Note we don't have to specify parameters or anything like that because any parameter of this linear layer will automatically be considered a parameter of any layer that includes it as well. Now we can define our forward function, and we can define this as return self.w2 applied to torch.relu of self.w1 of x. Okay, and now what we can do is actually apply this to x. So let's make a model, which is a 2-layer neural network with the input dimension, again, 128, maybe output dimension 56, and I don't know. I'm just going to pick a non-power of 2 here for simplicity. 500 is our hidden dimension. Then we can apply our model to x, and we get a tensor, which is the exact same size as it was for our linear layer, to be clear, right? Because this is our batch size and the output size, but it's transformed by first applying the first layer, then applying a ReLU, then applying the second layer, and that's how we actually get the values in this output here. Okay, one last thing before we go on. There is one little sticking point that might come up already in the first homework, which is the following. As we saw here, oh, and I should also mention, just to emphasize this point. So if I look at the model.parameters, I mentioned this before, but I didn't actually show it. If we look at all of these, there's actually 2 elements here. So the parameters of the first linear layer and the second linear layer are all contained in the parameters, or all returned by the parameters call of that full neural network model. All right, so it essentially tracks the parameters of all sublayers. Okay, one little hiccup which you might encounter, which I just want to show briefly here, is if you embed layers. So again, PyTorch layers, PyTorch modules track the subparameter, their module subparameters. The one exception to this is if those subparameters are in a list or in a dictionary. We're not going to worry about dictionaries for a second, but let's just talk about lists. So if I were to define the layer instead like this, so I'm going to have one linear layer, and this is something you might want to do, say, when you have, a arbitrary layer neural network or something like this. So now what I would do is I would return this, W1 would be my second layer, and W0 would be my first layer. So this is a perfectly reasonable model, of course, right? It can return the same output. But now it turns out that if I look at parameters, I have no parameters here, right? So this parameters actually returns an empty list now. This is because PyTorch does not track parameters within lists within that module. And so in order to make that happen kind of the way you expect, there's one more import you need to do. I'll actually just import it down here. And we will import this for you from in the homework. We'll sort of pre-import this library just to remind you. But there's this sort of nice container module list. And if I wrap my list in a module list, now it actually is going to properly track the layers. And so this works the same as before. Oops, what happened here? Oops, sorry, module list. There we go. So we're going to wrap this in a module list. And when we do this now, the layer will work the same as before. So you can still access each element just by W0 and W1, etc. But now the parameters of all these things are actually tracked. So when you have a list of layers in your module, you're going to want to use this module list. I will mention one more nice property of modules. There's really a lot that are nice things before we break here, and that's the fact that modules can also be very handy at shifting data over to either the GPU or changing the data type itself. So if we look at, let's look at, in fact, just this parameter. So if we look at the model parameters, and let's look at the first element. Model list model.parameters. Look at the first element. That we can look at sort of the type of the floating point type that's used to represent this model is a 32-bit float. That's the default for PyTorch. It will sort of be the standard. And it's typically, at least for this class, we're not going to worry about other types. But there are issues. There are times where you want to, say, convert this maybe to 16-bit floating point, or maybe you want to convert it to 64-bit floating point. And one nice thing about modules also, and when you do that, you often want to sort of do it for all the parameters of a module. So model also lets you do things like convert the type of the modules. This, for example, converts this to 16-bit float. Or I could say model.double, that will convert it to 64-bit float. And the point is, this will actually do it for all the sub parameters of the model. So you also have the nice ability to kind of use this, and the same, by the way, we won't do it right now, but later on when we use GPUs, the same can actually be done to convert the entire model over to be stored in the GPU and things like that. So it's very convenient to have this, all your layers built with this module, built as subclasses of this module type. And we're going to do this kind of throughout this course. Okay, so that actually is all you need to know about PyTorch, at least to complete the first assignment. We are going to, in fact, have quite a bit more, sort of aspects that you will deal with PyTorch. You'll build like a data loader and things like this. But there's going to be several other aspects of PyTorch that you will cover in the homework, but these are the basic principles, and they're enough to get you started on the homework. In fact, the first question on the homework essentially is just going to ask you to implement this layer here. So there's lots that you will learn in the homework. You'll also build an optimizer kind of in the PyTorch standard, and you'll work out a way to sort of train both linear models and simple neural networks kind of within PyTorch. And altogether, that's sort of a very, very nice set of things we can now do. In fact, at this point in the class, we are done talking about sort of the whole first part of the class, which is on basic supervised learning. So I'll just sort of mention here as an accomplishment point, this is the end of part 1 on supervised learning. supervised machine learning, I should say, supervised machine learning. You've now learned, and again, it's good to take stock of it. You've now learned everything you need to know to train a simple machine learning model, or maybe not that simple, right? A model like a linear model or even a neural network on basic classification problems, right? So classifying images of digits, say. But by the way, you can also apply those same things to classifying images of simple shapes and other things like this, or maybe sounds, or a lot of other problems can actually be solved just with the techniques, simple, fully connected network, the techniques you've already learned so far, and that you will have learned once you complete the homework 3. However, it is also the case that modern AI systems like ChatGPT, Claude, Gemini, LLMs broadly, also, I should mention sort of real image classification examples. So if you're actually driving, a car, a self-driving car, the way that those vision models actually work. These are not covered by what we've learned so far. We've learned sort of very simple functions that take single inputs and map to single outputs. What we're going to start in the next section is to talk about large language models, which are an instance of more structured input models that take a more structured type of input, in that case kind of sequences of text. But structured inputs are very broad, and really every real sort of AI model you see typically in the world uses some sort of more structured input, whether it be vision methods, voice recognition methods, or in fact large language models. So in the next class, we are going to start our section on large language models. And we're then going to start building up a slightly more expanded set of machine learning models that is able to capture more complex relationships as they occur in structured data. And this will in fact form the basis for models like chatbots, like the AI you deal with every day. So that's going to be the agenda coming up next lecture. Congrats on finishing the first part. Well, I should really say, if you finish the first 3 homework, I guess first 4 homeworks, you will have finished the first part. Congratulations, and I hope to see you soon in part 2.